exact differential. If we have a function z is a function of x and y, we can write the change in z to be partial derivative of z with respect to x times the x plus partial derivative of z with respect to y times the y. Z can be written as p dx, where this is p, plus q dy, and this is q. Now, p is partial derivative of z with respect to x, keeping y constant, and q is partial derivative of z with respect to y, keeping x constant. So what we want to do is to find the partial derivative of p with respect to y, keeping x constant. And I can write that as the operator here, the partial derivative with respect to y, and then I'm going to place this p here. So that's the p, this operator here, and p is this. Multiply that with that and multiply these together. So we get partial derivative second order to power 2 of z with respect to y and x. And that's how I get that. I'm going to do the same for q. Partial derivative of q with respect to x, keeping y constant. And that will be equal to, then I'll write the partial derivative with respect to x. And I'm going to put q, which is this, here. And that's q. When I multiply them together, that times that, and then that times that, we get partial second order to the power 2 of z with respect to x and y. If you notice that that is equal to that. So that partial derivative of p with respect to y is equal to partial derivative of q with respect to x. Because they're equal, we can write this expression, and that is the test for the x to be exact differential equation. If the function of z and the z obeys this rule, that means it's an exact differential equation. But it has to obey this rule, so you have to test this to be able to show that. Here's an example. Test for exact differential. We got this. dz equals to 3x squared plus 4y squared dx plus 8xy dy, which means that this is dz when that equal to p, so that's p, the x, that's the x, plus q, that's q, dy, this is dy. So we write the p down. I want to find the partial derivative of p with respect to y. That means I need to differentiate this with respect to y. All right, partial down, and I'm distributing it here. 3x squared plus the partial again, 4y squared. 3x squared will be a constant because there's no y. I'm differentiating with respect to y, so I have to take that out. And there'll be 1 left. 3x squared times 1 is 3x squared. Because I've taken 3x squared out, 1 is left. Plus, now there's y here, so I can leave that, but I can take the 4 out. 4 partial and y squared. Now I need to differentiate this. Because there's 1 here, and I'm doing with respect to y, I can write that 1 is y to power 0. Y to power 0 is 1. I'm differentiating this. If I'm differentiating that, I put 0 here, and I get 0 times 0 minus 1. Because I'm timesing it by 0, it will disappear. So that will disappear, which means it will be 0, which means that will disappear. Because that's 0 times that. So I'm going to get that y to power 0 plus 4y to power 2. If I differentiate that, I'll get 0. 0 times that is 0. 0, that's what I get here. And that times 0, that'll be 0. Plus 4y power 2 will be 2y, 2 minus 1. 2y to power 1. And that will be 0 plus 8y. The partial derivative of p with respect to y is 8y. Now we need to find it for q with respect to x. And if they're equal, then the function is exact. Now for q, which is 8xy, partial derivative of q with respect to x will be the partial derivative with respect to x. That operator will be operating on q, which is 8xy. Because we're doing it with respect to x, y is constant, so I can take it out, and 8 is also constant. So 8y will be taken out. We then have partial derivative with respect to x of x. When you're differentiating x to the power of n, the differential will be n x to the power n minus 1. In this case, x is 1 to the power 1, so you put 1 there, and that's 1 times x of to the power 1 minus 1. 1 minus 1 is 0. That will be 1 times x to the power 0, and that's 1 times 1, and that's 1. So this will be 1. Looks like you could cancel it out, But if you operate that on x, you get 1. Partial derivative of q with respect to x then equals to 8y. We know that the partial derivative of p with respect to y is also 8y. Therefore, the z is exact differential. Here is some exercises to do. Pause and try this test for exact differential. Question 1 and question 2. For question 1, the z is exact differential. And for question 2, the z is not exact differential.